Hello and welcome to another video. In this video, we're going to be doing arithmetic slices to subsequence. And in the problem, you're given an integer array nums and you want to return the number of all arithmetic subsequences of nums. Subsequence of a number is called arithmetic if it consists of at least 3 elements and if the difference between any 2 elements is the same. So for example, these are arithmetic subsequences because these increase by 2, these stay increase by 0, and these decrease by 4 at every single location, and this one's not. Subsequence is a sequence that can be formed by removing some elements, possibly none. So let's take a look. So here, all arithmetic subsequences are all of these. And here, there's a bunch, basically, like any 3-length sequence is 1. So like this is 1, this is 1, this is 1. And then every 4-length sequence is 1, and so on and so on. And you can also get rid of numbers, so something like this would be 1, and so on. So what we're going to do is we're going to start with an easier version of the problem, and then we are going to go to this one. So let's say we have some numbers, and let's actually use this 2, 4, 6, 8, 10. So let's just have an array. We'll have 2, 4, 6, 8, 10. And then we'll have like a DP array as well. And I would definitely recommend doing a longest increasing subsequence, I think it's called, first, before this one, because it's going to use similar things. So let's say we have 2, 4, 6, 8, 10. And in the longest increasing subsequence, you're basically asked to get like the longest increasing subsequence ending with some number. And so if you recall, that strategy, the DP variation of that is basically for every number, you just check the previous numbers and you check like, is that number bigger than the previous number? If it is, then I can take whatever sequence a previous number had and add this number to the end. So for example, if I'm on 6 and I am checking like what numbers can this follow, I can go to like 4 and be like, okay, well, 4 has a longest subsequence of some length. Let's say 3. Let's say my subsequence was like 1, 3, 4 or something. You don't really need to know what it is. If 6 is greater than 4, then I know I can easily just put the 6 on the end of the 4, and then my sequence with the 6 is going to be whatever it was with the 4 plus 1. So it's going to be kind of a similar idea. So let's try to figure out how we can get the longest, or actually instead of the longest, let's go for the number of subsequences that are length 3 and increasing. Let's do that, right? So we're looking for subsequences that are length 3 and increasing. For example, like 2, 4, 10 would be 1, and so on. So let's figure out how we do that. So it's going to be kind of the same idea as the longest increasing subsequence for the number. So basically what we're going to do is the same thing. For every number, we're going to loop through numbers before it. And we're going to check, is that number bigger than those numbers? And if it is, then we know that however many sequences that one had, we can always just add it to the end. So for example, let's say 2 had a bunch of sequences. We don't really need to know what they are. We just need to have a count. Let's say one of them was like 1, 2. One of them was like 3, or not 3, 4. 0, 2, negative 2, 2. And we are on 6. We can kind of do the same thing. We can say like, well, if 6 is bigger than 2, we can take whatever subsequences were in 2 and just add a 6 on the end, right? So we can take that number and we can get it and store it. And we'll have a result variable as well. So let's have a result variable. Okay. And so what we're going to do, and we also are going to show how we can get subsequences of length 3. This part's a little bit tricky. And then we're going to use the same example for the arithmetic part to solve the actual problem. So first for 2, there's really nothing, right? There's nothing to the left of 2, so this is just 0. Then we're going to go to 4, and we're going to check every number to the left of it. Is 4 greater than that number? And if it is, we're going to add a 1, right? But we want to make sure that we have subsequences of length just 3 or more. So for example, we're going to say, is 4 greater than 2? Yes, it is. Okay, well, let's add a 1. Because 2, 4 is a subsequence, right? But it's not long enough. So the way we're going to handle this is for every number, we're going to check, is 4 greater? If it is, we'll add a 1. But then we also are going to check, are there actually any subsequences with the previous number? And if there are, then those are ones we can use. Because the subsequences with the previous number are going to be length 2 or more. And then when we add 4, those are going to be length 3 or more, right? So this 2 has nothing. So this 4 is going to have nothing. Like there's nothing 2 doesn't have any subsequences, so we're going to leave it like this. And we're not going to add this 1 to the result because even though 4 is greater than 2, this subsequence is not long enough. So let's keep going. And this is basically symbolizing, we can write this below it, subsequence of 2, 4, right? We just have 1, it's not long enough. Now for 6, we're going to do the same thing. We're going to check, okay, is it greater than 2? Yes, it is. So we'll add a 1 here. And are there subsequences that end with 2? No, there's not. Now we're going to check 6 and 4. Is 6 greater than 4? Yes, it is. So we'll add a 1. So once again, these subsequences that it's symbolizing is 2, 6, and 4, 6. And is there a subsequence that ends with 4? Yes, there is. Remember, it's this 2, 4. So we know that 2, 4, 6 is 1. Right? So now, because there is one that ends with 4, we will add that as well. And this is the one that we'll add to the result. So now the result has 1. Then we're going to go to 8. And we'll make this all a little bit bigger, just so we have some space. Okay. So I'm actually going to get rid of these. Like now that we know there are some, I'm not going to keep track of these. But essentially, all these subsequences that are stored are length 2 or more now that we know that. There we go. So, and let's move this over here. So now on the 8, we're going to do the same thing. We're going to check, is it greater than 2? Yes. So we'll put this as a 1. Are there subsequences that 2 ends with? No. So 2, 8 is a subsequence, but it's not long enough. Now we're going to check 8 and 4. Is 8 bigger than 4? Yes, it is. So this is going to be a 2. Now, is there a subsequence? How many subsequences have an end of 4? There's only 1. So, and there was this like 2, 4, right? So what we're saying is 2, 4 with an 8 is going to work. Right? And so here we will add 1 to the result. So this will be 2. So basically, anytime our number is bigger than something, we add a 1, but we also need to check, is there something stored in that other number? And if there is, those are the things we add to the result. And that's going to ensure that our subsequences are length 3. Then, yeah, so this should be 3 because 8 is bigger than 2, 8 is bigger than 4, and 4 has 1. So it's 3 total now. Now we check this 8 and 6. Is 8 bigger than 6? Yes, so we'll increase this by 1 again. So 4. And are there subsequences that 6 ends with? Yes, there is. There's 3 of those. So those are the 3 that we will add to the result. And we will also add them here. So 7. Then we go to 10. And there's a bunch here, right? Like we can draw a bunch of these out. So a bunch of subsequences that 6 ends with would be like 2, 6, 2, 4, 6, and 4, 6. Right? These are the ones that 6 ends with. And notice that any subsequence that is in here, we can always add an 8 to the end to make it valid, right? 8, 8, 8. These will always be long enough. So that's kind of the idea. If there is something stored, then those are the things we're going to be adding to the result. But we do need to add the 1 initially because we do want to also store subsequences of length 2, but we don't want to add them to the result until we're comparing that, like we're comparing the number to the number before. So for 10, we're going to do the same thing. Is 10 greater than 2? Yes, it is. So we'll add a 1, but that's not long enough. So basically 10 is going to be greater than all these 4, so we can just add a 4 right away. It'll be a 4, right? But none of these subsequences are long enough, like 210, 410, 610, 810. Those aren't long enough. But for 10, we can also add it to the end of all of these, right? So we would basically add 1 and 3 and 7, and this is what we would add to the result. So we would get 11 plus 3, which is 14. And we would add the 11 here, so 14. Actually, I don't know if I did that right. Let me go back here. Yeah, I think that's right. It seems like it. Maybe I did the math wrong, but the idea is still the same. So essentially, we can write this down. So compare number to all previous numbers. If it's greater than the number, add 1 to its count. And if that number has a count, add that count to result and to current numbers count. That's kind of the idea. Now let's take this and let's change this into the problem that we are actually solving. So we're going to go back to the problem that we're actually solving, which is this we need arithmetic subsequences now, right? We don't just want like anything. So let's figure out how we would do this. And it's a small change. It's not that bad. So here we're going to use this 2, 4, 6, 8, 10. Now for a subsequence to be like, before we were looking for subsequences that were increasing. Now we're looking for subsequences with a common difference, right? So for something to be part of a subsequence or to be added on, like before, if we had a subsequence of like 2, 4, 6, and we were on 8, we can just add it on because it's bigger than 6. But now what's our criteria? So now our criteria to add a number on is have a subsequence. Let's say 2, 4, 6 again. Now our criteria to add on the number is have a subsequence. We need to know the difference between every two numbers. So in this case, it's 2. And then we just need to make sure that our number that we're trying to add on is the same difference from the last number, right? So we don't need to store subsequences. We can just store a dictionary for every single number. And the dictionary will have a difference, right? The difference, like what are every two numbers difference in, and count. And so we can kind of walk through this again and show this. And that's basically what we would need to do this, right? We just store the difference, like what difference do we have for each number, and then how many subsequences are there. And then for every subsequence, like let's say we have subsequences with a difference of 2 and there's like 5 of them. And we are on that, like let's say that's here, right? Here, there's somehow this thing. Then when we go to 4 and 2, we will say, is 4 greater than 2? Yes. So that difference is 2. So we will add 1 to 4, same thing, right? Difference of 2, add 1. And that's going to be a subsequence of length 2, kind of like what we had before, which is 2, 4. But then we will also check, now that for this difference, are there subsequences in 2 with this difference? And those are the ones we can add to the result. Because all 5 of these are length 2 or more, and then we can add a 4 to the end of those, and those will be valid. So that's kind of the idea here. So let's actually do this. Hopefully we get the math right and get the same as the result. So for 2, there's nothing before 2, so this is just going to be empty. Then for 4, and let's actually probably make these a little bit bigger because we're going to have dictionaries now instead of just a number. Yeah. And we'll still have like our result variable. And we can probably actually get rid of this part so we can make it even bigger. There we go. Okay, so there we go. And let's have a result variable like we did before. Make it 0. And I'll just write a number instead. So 0. Okay, so for 2, right, let's actually use an arrow as well. So for 2, there is nothing before it, so we don't do anything. Then for 4, we're going to compare it to every number before, and we're going to say, okay, what's the difference between 4 and 2? The difference is 2. So we know that for a difference of 2, there's one number, but recall that this is not long enough, right? It's just 2 numbers. So we're going to check, is there something in 2 with a difference of 2? No, there's not. So then we're going to move on over here. And we're going to compare 6 and 2 first. So the 6 and 2, there's a difference of 4 with a number of 1. Okay, is there something in 2 with 4? No, there's not. Now, 6 and 4, there's a difference of 2 with a number of 1. Is there something in 4? Yes, there is. There's this one over here, and that was 2, 4. So this is the one that we can add 6 to the end of because 2, 4, 6 would be arithmetic. So then we'll change this result to a 1 now. And we will add this value over here, right? So this will be 2. Then we go to 8. We compare 8 with 2. There's a difference of 6 there. So difference of 6, value 1. Is there anything in 2? No, there's not, so we don't have to do anything there. 8 and 4, there's a difference of 4. Is there anything there? No, there's not. 6 and 8, there's a difference of 2, value 1. Is there anything in there? Yes, there's 2 of them. So these are the 2 that we will add here. So this will be 3. And we will add it here as well. Okay. Now we'll go to 10. Compare to 2, difference of 8, value of 1, nothing in there. Compare to 4, difference of 6, value of 1, nothing in there. Compare to 6, value of 4, there is 1 in there, right? So 4. So originally there's a value 1, but there's this other 1, and that's the one we're going to add to the result. So this will be 2. We add this to the result, and that would be the subsequence of 2, 6, 10, right, which makes sense. Then we compare it to 8, a difference of 2, so value of 1, And how many are there? There's 3 in here, so we'll add those 3 to the result. So now we'll have 7, and we'll have 4 in here. And so we will have 7 subsequences, and if we actually go back, then we do have 7. So it is kind of tricky to figure out this difference thing, like to maintain a difference, but doable. And I do think this is one that bottom-up DP is easier. And the reason you want to go for DP, I think I didn't talk about this in the beginning, but pretty much everything that you can delete elements from is going to be like at least 50% DP, right? So if you can figure out DP, then do it. And like I said, this is kind of similar to longest increasing subsequence, because for every number, you have to check the number before. It's a lot easier to do this bottom up, in my opinion. Like, I don't know what the memorization for this would look like, but I would rather not do that. So yeah, very rare that bottom up is better, but in this case it is, in my opinion anyway. So now we kind of have everything we need, so we can code it up. So we're going to have a DP array, and every single index will just have a dictionary. Yeah, so we're going to use a default dict of int, and it'll be empty at first, so we can just make a bunch of dictionaries that are all empty. Now we'll have a result, and then we will have a nested loop, right? So the first loop will just loop through all of our numbers, and the second loop will loop through every number up to the current number, and we will check them. So we'll get a difference of the current number and the previous number. We will add it to the dictionary of the current number, so dpi difference plus 1. And we will check, is this difference in the previous number? And if that difference is in the previous number, let's get that count, and that count we can add to the result, because all those subsequences are at least length 2, and we can just add this number to the end of all of them. So if d in dp j, then result plus equals dp j and that difference, dp. This is like using variables with as little characters as possible. And we also need to add it to our actual array or our actual dictionary that we're on now, right? Even though we're not adding this to the result, all of these will be valid for numbers that are later than it. And then we can just return result. So not a lot of code, pretty simple. I do think it's hard to come up with these states, and I do think bottom up is way easier. So definitely would recommend it for like these types of problems. And apparently it's wrong. So let's double check what I did wrong. J. Oh, this should not be +1. This should be plus equals. Okay. Hopefully that's right. Okay, there we go. So pretty efficient. So yeah, time complexity. So if you think about it, we are, whoops. This is going to be n squared. And for every single comparison, we're only accessing one value in the dictionary. So even though something might have a lot of values in the dictionary, when we compare I to j, we're only comparing this like D location. So this will be fine. And we're only updating a dictionary value when we're comparing to some other thing. So basically you're only updating one dictionary value in each iteration of this loop. So this would be n squared. And for the space, so I think this would be like n squared as well, because you have n dictionaries, and worst case scenario, like imagine your numbers are all increasing by some different amount, right? Like by 1, then by 2, then by 3, then by 4, and so on. Then you would basically have like n differences for the last value. So your dictionary length would be n and for the last value. So yeah, I think it's gonna be n squared time n squared space. And yeah, kind of cool problem, honestly. I think it's pretty good. And yeah, so hopefully this was helpful. And if it was, then please like the video and subscribe to the channel. I'll see you in the next one. Thanks for watching.